Welcome. In the previous videos, we looked at the groundwater flow equations. The previous video, we looked at the analytical solutions. In this video, we're gonna learn. Remember, I told you can solve it analytically, numerically, or graphically. In this video, we'll look at the numerical solution and why can this also be useful. Yeah. Okay, so let's get started. So by the end of this video, you should be able to draw equipotential line and flow lines. So remember, equipotential flow lines are generally perpendicular to equipotential line. And then we will do this for homogeneous and anisotropic cases. Yeah. So we talked about so this is the governing equation. So that's, for example, what mud flow solve numerically. So in our project, we will solve this equation numerically using MudFlow. And MudFlow, or not MudFlow, like numerical solution in general, that is the one you use for any most real cases scenario because you don't have any restriction. You don't have simplified assum restriction. You can account for any boundary condition. You can account for any geometry or shapes or things like that. Yeah. Analytical solution, they require some restrictive assumption, as we have seen. Yes, we made some assumption in order to find an analytical solution. Analytical solution could be a closed form, like what we got last time. Closed form is the equation. You substitute in it, you find your head, for example. Or it could be infinite series. That's another form of analytical solution. Yeah. Graphical solutions, similar to analytical solutions, they require also restrictive assumption. And usually we do graphical solution just for visual understanding. Yeah. And you can also do some quick calculation from them, as I will show you. Yeah. Okay. So here, so why do we do like this graphical solution? For the flow system to be intuitive. And by the way, graphical solution, not necessarily like we do them by hands all the time. Sometimes you can do them with software. There's software for that. And if you check one of the books that I recommended for this, you will find like information about these software. So let me go here. Where is that? Yeah. So yeah, this one. Like you see this book here. If you want to, oops, if you want to learn more about graphical solution, you can check this book here. Right. So let's go back. So graphical solution. This is to have like an intuitive understanding of the system. Uh, so and that could be just useful to, for example, understand where would be like some preferential flow passes. And I will like show you an example. Yeah. And graphical solution, as I will also show you in this video, you can also use them for some initial assessment. So like you will understand your flow and you can even quantify this flow. Yeah. So some for initial like back on the envelope assessment, you can also do this uh, graphical solution. Yeah. And this like graphical solutions, they will also help you to assess, for example, intuition regarding level of numerical groundwater model. So let's just look at some of not a graphical solution, but let's look at some like just visualization like this for the first point, because usually when you visualize this system, you understand them better. Yeah, that's how you understand these system better when you visualize them. So let's look here. This is dye water moving through a tank. So I think in this experiment, some dye will be injected. I think you guess from here, and then we will see where this dye will flow. So this is just because remember in the previous lesson I showed you a lot of graphics, because from this graphics you develop your visual understanding about hydraulic head. The more you see this graphics, the more you will develop your intuitive understanding about these flow system and how the flow occurs in nature. Yeah. So here, for example, if we injected some dye here, my intuitive understanding, like here's a head, I am assuming that he had like, it depend, like, see, where is the head here? So like you look at the head and then you determine where the flow direction is. So if the flow direction is here from high to low head, my understanding, if I injected the dye here, it will end up going somewhere here and like discharging from here, because nature generally move from the path of least resistance. So electricity move from the path of that has less resistance, and same as water, like it move from the path of least resistance. Electricity, water flow, current flow, uh, that's the nature of nature. It like move to the path of least resistance. And so my intuition is that it will move here. Let's see, yeah. But uh, let's look at this video and see how it will go.
This physical model of a groundwater system includes layers of gravel, silt, and sand representing the subsurface. Water flows into the tank from reservoirs on the left and right that are maintained at a constant water.
So you see here, these are the gravel, and these are the sand, and these are the silt. So water will generally like move to this gravel. That's my expectation, because that is, remember why? Because this has the lowest hydraulic conductivity. This and this one, sorry, this has the highest hydraulic conductivity, and this one, like the silt, this one has the highest hydraulic conductivity. So, and this is like a confining layer, and that would be a confined aquifer. So that would be an example of an unconfined aquifer, and that would be an example of a confined aquifer, and this is a confining layer. And see, this unconfined aquifer, it has some silt lenses in it also. Okay, so let's continue watching the video.
Level. An outflow tube about 3/4 of the distance from the left side of the tank represents a location where groundwater discharges to a stream. Wells penetrate the porous materials at various locations and discrete depths. Some of the groundwater flow is revealed by adding red dye to a well. The moving shadows are our reflections as we film. Flow from the left carries the dye slightly upward to the right. The upward component is caused by diverging flow exiting the gravel lens to the left. The flow path reaches a high point, then turns downward as flow converges on the gravel lens to the right. Groundwater flow is slow, so this video compresses 30 minutes of time into 1 minute of video. When the dye reaches the gravel lens, it moves more rapidly because the groundwater velocity in the lens is higher. Next, green dye is added to a deeper well below the silt layer. The green dye moves upward and to the right because flow is converging on the gravel lens that connects to the stream. As time continues and no more dye is added to the wells, the concentration of dye in the water decreases as revealed by the fading colors. Although it took only a moment to introduce dye to the flow system, days of flushing with fresh water will be required before all of the dye has been removed.
Monday.com, the opposite of any work platform we tried in the past. We tried other work management.
Okay. So yeah, so you see here now you get like, once you, this is just like, I was just showing example for like having an intuitive understanding of the system. But another way is that also we do this for rapid initial assessment. So we can draw like flow lines and equipotential line, and that will give us we will can do some quantification of the flow. So let me show you an example of something that you can this is again a video, but like this is like by the end of this video you should be able to draw these flow lines that you will see in this video on your own. Like, so let's watch this video. We did this example before, remember, like in the last video we did analytical solution. That was like an island. I told you like there's an island and there was an ocean here and there was an ocean here, and then you had like some recharge from the top. So that's exactly what's happening. You have like recharge here from the top, and the water, remember I told you there will be groundwater divide, and you have a homework problem to solve about this, where there is like a groundwater divide, and you know where the groundwater divide is. And then after this groundwater divide, some water will flow to here and some water will flow to here. So let's just visualize this.
This is a Healy-Shaw model that represents groundwater recharge on an island that flows to a surrounding lake. A Healy-Shaw model is two plates with a small.
I want to show you, see, like water here is diverging here, and water here is like diverging or converging like to here. And you see here in the middle, this is where the groundwater divide, where there is no flow. So either water will flow here or water will flow here.
Spacing between them that is filled with viscous liquid. Flow lines in a Healy-Shaw model follow the same principles as flow lines in a homogeneous porous medium such as sand. The configuration of the plastic model includes a no-flow boundary on the bottom as well as along the curved surfaces on each side.
So here, this is a no-flow boundary, this is a no-flow boundary, and this is a no-flow boundary.
There is a constant head boundary along the top where recharged water enters the system. The water level.
So here, this is a constant head boundary. So head here is equal to anywhere here. This is the same. And also here you have a constant head boundary, and here you have a constant head boundary.
The level of each side reservoir is controlled by adjusting a valve that determines outflow to the lake and thus the water level in the reservoir. The die shows the path of water flow from where it recharges at the surface to where it exits at the lake. We can see that the valve on the left is allowing slightly more outflow than the right because the die advances more rapidly on the left. Although water levels in the side reservoirs appear to be the same, the level in the left reservoir is actually slightly lower than the water in the right. I backed up the video so that you can watch that portion again. We can tell the difference in flow rate to the left and right is not large because the groundwater divide develops close to the midway point between the reservoirs. For each side of the system, the difference in head from entry to exit is the same for all flow paths. The head difference is equal to the water level in the upper reservoir minus the water level in the side reservoir. Although the head difference is the same for each flow path, the velocity of flow is higher along the shallow flow path because the distance between the heads is shorter, so the gradient is steeper.
I want to know,
Okay, so we will learn in this video how to draw these flow lines and this flow net for a case like something like this. Okay, so what are, remember for the analytical solution, we have some restrictive assumption like boundary condition are known, like constant head boundary, for example, or whatever. Aquifer is homogeneous. Isotropic, steady state flow, Darcy law is valid, fully saturated groundwater zone, and incompressible soil and water. So that's the same assumptions that we had for the previous examples that we solved for analytical solution. Okay, so what are the steps to construct flow net? So there are like steps to do this. And the first step would be to identify and draw your boundary condition. Uh, that would be the first step. And like what you can see here. So here, this is a constant head boundary. Let's say this is, oops, uh, this is like 10 meter, for example, and this is like 2 meter. Yeah, that's like a constant head boundary, yeah, or whatever, or 0 meter or whatever. Yeah, and then here you identify this is like no flow boundary. Yeah, so this is no flow boundary. So first you identify you identify your boundary and then you draw them to scale. Yeah, sketch the boundary to scale, and then remember, this is a constant head boundary, and flow line would be what? Like they are perpendicular to this one. Yeah, so that would be perpendicular here. That would be perpendicular here. This would be like perpendicular here. This will be like perpendicular here. This because flow direction is from high energy to low energy. This would be perpendicular here. This would be perpendicular here. So that's the thing. So that's the second step is like to identify like a flow line and then you draw like some set of flow lines. Yeah, and then you draw a set of equipotential line. Equipotential line would be perpendicular to flow line. And the thing is, like when you do this, this needs to be square. So like you need to have like square here. Yeah, this needs to be square. This needs to be square. See, this is not really a square, which means that what do I do? Then I have to erase it and just like draw it again so that I will make it like maybe this. Oops, maybe this one and maybe just this one. Then I can not really square. Yeah. So that's the thing. Like you have to that need to be square. Yeah, so okay, now maybe something like this. This is square or like curvilinear square because sometimes you cannot make perfect square, so you can they will be curvilinear square. Okay, so basically like you draw your flow line, you draw your flow net, draw a set of flow lines, draw initial trial set of equipotential line. The equipotential line should be perpendicular to the flow line, and then erase and redraw until like you make squares. Yeah. That's what you're doing. It's fun, yeah? You make square here. Yeah? Square, square, square. Okay. That's basically like the steps of how you do it. But what are these boundary conditions? We talked about boundary condition. Let's talk about them one more time. Yeah. So boundary condition, you have like a specified head boundary. So the specified head boundary, this is like here, yeah? So like a constant head, for example. So the boundary here, which I'm specifying is that like head here is constant and is equal to 10. So this means that head here is 10 meter and here is like 10 meter. And here is 10 meter, here is 10 meter, here is 10 meter, here is 10 meter, anyway. And then now the important thing is that as I told you, flow line will be perpendicular to to this specified head boundary, which is an equipotential line because this head here is constant, yes, 10. So that's an equipotential line. So I will just make a flow line here that's perpendicular to it. Oops. I'll just make a flow line here. Like this is what you need to know. Like the flow line will be perpendicular. Similarly here, like you have like a flow line here will be perpendicular. Flow line here will be perpendicular. Flow line here will be perpendicular. Yeah. So that would be an example of a specified head boundary. Type 2 is no flow boundary, like zero flux boundary. Like for example, no flow boundary, an example is like you specify the flux, the amount of water that's passing in time would be zero. Yeah, that's, I mean, that would be also a no flow boundary. And for the no flow boundary, so that's a no flow boundary here. Yeah, so that's like water does not flow like this. This is a no flow boundary, so it does not flow like this. So that's here is a no flow boundary. And what you need to know for the no flow boundary is that flow line will be parallel to the no flow boundary. So you see here, this one is parallel to this one. Is like it would be parallel to the no flow boundary. Again, so we have type 1 boundary condition, a specified head boundary, flow line will be perpendicular. No flow line, no flow boundary condition like type 2 boundary condition, when I specify that the flux is 0, then the flow line will be parallel to this one when you have like a no flow boundary. Yeah. And then so here what would be at but the flow line would be parallel, but equipotential line will be at a right angle. So you see here, this is the equipotential line. These are at a right angle. Like, yeah, here, see all these are at the right angle. So that's here, that's again, that's also a no flow boundary. See, that's a no flow boundary. All this is a no flow boundary, and this equipotential line would be at a right angle here. See, it's at the right angle. So that's it. That's how you draw like these guys. Yeah, that's how you draw these guys. Another type of boundary that you will get in this system is like water table. So water table, what is water table? Like water table is neither like a it's neither it's not a flow line and it's not an equipotential line. Yeah, because head is not necessarily constant. Like you see, head here, for example, is 25 head here is like 24 here, heat is 23, 22. So it's like it's not an equipotential line. It's not also a flow line because the water will in that case water will flow in this direction, yeah, because you don't have recharge. So if you have like no recharge, like in this case, the flow line will coincide like with your water table. But in that case, if you have recharge, see the flow line, see that's your flow line, that's your water table here, it could be perpendicular to it. If you have a recharge and you have a vertical component. Without recharge, they could coincide together. So water table, it is it will be like not necessarily perpendicular, it could be also oblique or at any angle. So that's like an angle here, yeah. That's like an angle here, not necessarily perpendicular, yeah. So in that case, it was just perpendicular, but it could be like in that case, it's perpendicular, but here it's oblique at a certain, like at an angle, yeah. In that case, it just coincide uh, with this one, with like flow line coincide with the water table because like recharge is equal to 0, yeah. Here in that case, like recharge is like greater than 0. So you have some recharge here, while here there's no recharge. Okay. So when you have recharge, water will flow from here, 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 and will flow to this one. And in that case, water will flow from here to here. And we saw this in the previous video already. And that's the no flow boundary. That was similar to the previous video, yeah? Where there was like no flow boundary here. And you see here your flow line is parallel to your no flow boundary. Here, your flow line is parallel to your no flow line. So that's all. That's all what you need to do. Uh, Here, this is just like I want you to practice again. Like we did this before, but I just want you to practice again how to like what is the water table, what is the equipotential line, and what is the flow line, and how they are different. Yeah. So for example, like at this point here, that's where your water table is. But like what is the head here? The head here would be like, so the water table at this point would be around like, I don't know, like at this point maybe like 70 something. What is the head here? The head here at like this point, at point E, yeah? What would be the head at point E? The head at point E would be 50. What about the head at point D? Like the head at point D, that would be uh, the head at point D. So the head here would be like 50, yeah, meter. The head here would be like something maybe like 75 meter. And the head here at point D would be 70 meter, yeah. So basically, like, what about the head here? The head here at C. What's the head at C? The head at C is 50, yeah. And what is the head here? The head here is 50. So that's an equipotential line. So you basically connect like these two guys here. Yeah. So that's like how you connect these two guys here. And then let's see what we want. Like if we want to draw like a flow line, so we draw something. The flow lines that should be perpendicular to here, and that should be perpendicular to here. So and then this will go like so. You started from here to here, for example, and you started from here to here, and that's how you draw this line. And see here, that need to be square. Like you try your best to do squares. See, you try like you keep doing this. Here, like some of these are curvilinear square, not a perfect square. Sometimes you cannot like get a perfect square, uh, but you try your best, yeah. And I will show you this next. Okay, that's how basically you draw this. Okay, so how to draw these guys, yeah? So you to draw these guys, uh, two things, yeah. Draw your boundary condition. We talked about it. Draw your and then after you sketch your boundary condition to scale, you sketch your equipotential line and flow line, and they must intersect at right angle. And you keep erasing and drawing again, erasing and drawing again until you find until you try to make like some square shape or or curvilinear square, and then you will have your flow line and flow net drawn. And from this flow line and flow net drawn, you can estimate Q, for example, as I will show you next. But let's just see. I will not play all this video, I'll just play part of it, but I want you to watch all of it. Yeah, it's a very nice video. Yeah, and it's the video like the one showing in this video is Eileen Poiter. She's the author of your textbook. She's one of the author of your textbook. Okay, so let's watch part of this video. I'm not gonna play all of it, but let's just watch part of it.
This video illustrates how to draw a flow net. The shape of the system shown here is similar to a plastic model that we show in another ebook video. It represents a concrete dam with an upper level and a lower level reservoir. The plastic model has a wall on this side, a wall on the bottom, and a wall on this side, and we will compare our flow lines to the flow lines of that model. So we've drawn a similar shape here. The white area represents homogeneous soil, and the black area represents a dam. The dam is wider at the base and has a cutoff wall, not only to provide some stability, but also to make the path of flow longer for groundwater moving from the upper to the lower level reservoir. To draw a flow net, we start by defining the boundaries, and this side is then an impermeable barrier, and the bottom is an impermeable barrier, and the wall on the right is an impermeable barrier. And with a flow net, we draw everything to scale. It doesn't matter how large it is, as long as everything is expanded or reduced to the same scale. We have to have a datum for the flow net, and for this we will use the base of the system. And this reservoir on the up gradient side is at 11 meters elevation, and the one at the down gradient side is at 6 meters elevation. We can define the boundary at the base of the reservoir as being an 11 meter equal potential line. We know that if the surface of a water body is 11 meters, then the head at any depth in the water body is also 11 meters. And so the equal potential line on this side is 6 meters. We know that there will be a drop of water that will theoretically follow the wall around the system and follow the inside wall of the dam around the system. There may be a bit of stagnation in the corners, and our objective would be to draw the central flow lines. So it's good to start just with your intuition of where do you think water will move through the system. Don't worry about getting it right at first, because the process of drawing a flow net is a process of drawing and erasing until you have a flow net that is acceptable. So I've drawn a couple flow lines. This would represent 3 flow tubes. There would be water flowing here, here, here. And in a flow net drawing, each flow tube is to represent the same amount of water flowing. We get that by drawing our equal potential lines in and making them at right angles to no flow boundaries, right angles to the flow lines, and forming squares between the equal potential lines and the flow lines. If I attempt to put in my first equal potential line here, I can see right away that I'm not getting squares in that area. So I would conclude that I probably have to move this flow line in somewhat. Maybe, and it must meet the equal potential line at right angles, and this equal potential line at right angles. So this one might move in a bit. We can judge whether a shape is square if we can roughly sketch a circle inside it. If it looks more like an oval, then it's not square. And I should say these are curvilinear squares. And in fact, a flow net does not have to have squares formed. We only need to make the same length to width ratio. It's just difficult to judge with the human eye a given ratio, but it's fairly easy to judge whether you have a square, so we work with the squares.
Problems are fun. How about this?
No, but
Let me continue to put equal potential lines in here. And a lot of times,
So I will like so basically what you will see in this video, she will keep like erasing and drawing, erasing and drawing, erasing and drawing, and so you can watch it in your own. I just want to show you like this part, and then after a set of erasing and drawing, I want to show you like you will end up with
109 cubic
I will show
meters
you
per
how to do
day.
this. Like I told you, you can calculate Q. I will show you how to do this. That's what she is doing.
If we wanted to know the head at any location in the system, we could pick a point. Let's say we pick this point. We'd estimate that this is about 1/4 of the way between these two equal potential lines. We know that the total head drop between equal potential lines is 4,545 meters. Dividing by 4, we'll say that's about 0.1. So the head at this location would be 0.11 meters less than 11 meters. So that would be 10.89. This is the system that we drew the flow net for. Notice the similarity of the lines indicated by the die and the lines drawn in the flow net.
Okay, so please watch this video. It's a very good like illustration of how to do this. So the link is here. You can find it in your slides, or just search for it on YouTube video, and you can subscribe even to this channel. I don't think I have a subscription here. That's a good advice. I should also subscribe to this channel. But anyway, that's how to do it. So here is an example. So here in this example, we sketched the no flow boundary. So that's like the no flow boundary. Yeah. And then, yeah, that's the no flow boundary. You sketch like your type 1 boundary, like a constant head boundary. So the head here is 100 and the head here uh, is this, and then you draw like a set of like a flow line and equipotential line. And since this is drawn to scale, as you've seen in the previous video, you can know like the head at each of these points. Like you can know the head here, 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 head here, because I know the head here and I know the head here, and then I know how many I have, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So basically, like you subtract like the difference, you divide them by 12, and then you will know like the slope basically. Yeah. And then you can estimate like the head here. Okay, so that is one thing. Like another thing, like you saw also in this video of where Eliane Poiter, what she did, she also calculated Q. Yeah, Q like flow, like Q total volume of discharge per unit width, for example, or big Q, or like Q prime or big Q, or even like. And how to do this? Like if you know the head, like so in this system, what do we know? Like we know the head, yeah. We know the head here, and we know the head here. So we know like the delta H, yeah. We know like the K, like the remember this is homogeneous, and we know the K, yeah. And in this equation, yeah, like if you know the head, yeah, and the K, you can calculate Q if you will get like these two things, like NF and ND. What is NF and ND? NF is the number of flow tube, and ND is the number of head drops. Yeah, that's simple. So how many flow tubes do we have? Like NF. So in that system, we have like one flow tube, two flow tubes, three flow tube. here, like you can see it here, like 1, 2, 3. Yeah, 1, 2, 3. We have 3 flow tube. How many number of head drop we have here? We have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14. So from here to here, we have 14. So ND in that case would be like 14, and NF in that case would be 3. And K is given, like K is given, and delta H, what would be delta H in that case? So delta H, that would be like 10 minus, and that will give you like 4 meter. Yeah. So basically, you substitute like here 3, here 14, here 4 meter, here K, whatever K is given, I don't know, like 1 meter per day, for example. Yeah. So you substitute here 1 meter per day, and then you get Q. If you know the aquifer width, like aquifer width here, if you know W, you can multiply this by W, and then you get big Q. If you assume W is equal to 1, then you just get Q prime, yeah, which is total volume of discharge per unit width of the aquifer. Yeah. Okay, so let's look at this example. So in this example, K is giving like 100 meter per day. Yeah. How many head drops do we have? Like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many flow tubes do we have? We have like 1, 2, 3, 4, 5, 6. Yeah. And you just like substitute this guy here, like K is giving, so K is giving, this is giving, this is giving. What is delta H? Delta H is 100 minus 80, you get like 20 meter. Yeah. And then giving this, you can calculate the flow rate per unit width of the aquifer. Okay. Oh, number of flow tube 6, number of head drop. I do a mistake here. Let's see. Oh, see, I have counting mistake. Uh, so like these careless mistakes are the most common type of mistakes that you find in exam, by the way. And like this careless mistake, counting mistake, copying mistake, yeah. So here I just did like a copying or like a typing mistake or whatever. Yeah, but that's 12. Yeah. Okay, 12 and 6. And then you will calculate Q as meter cube per day per meter per unit width. Here, this is like another example, and again, what do you do here? So what do you do here is that like you first define like your boundary conditions. So here you have like no flow boundary. You draw this to scale. Remember, like you need to draw this to scale. So this is like no flow boundary, no flow boundary. And then this is a constant head boundary, and then you can start like, again, I'm not going to do it here. Like you can watch the video of Alan Puter. I'll just like quickly do it because here I cannot like do a lot of racing. But see, that's like your initial guess of like how the flow will occur. So you'll have some flow will, sorry, this is a no flow boundary. No, sorry. This is a no flow boundary. This is a constant head boundary. So let me be more careful than that. Like so, you do this here, for example, like you do this here, you do this here. See, it should be perpendicular to this one. It should be parallel to this one. So your flow will be something like this, and your flow here would be something like this. And then you try to do your equipotential line. See here, I cannot make like a good square here. So this means that maybe I'll just do something here. Something here, maybe here. Cannot also, maybe I do something here. See, because you need to maintain good square. Then maybe that's okay. Yeah. Okay, something like this, yeah. Again, this is like I need to be more careful than that, but uh, so you can do this in that case, like in that particular drawing that I have, how many like flow tubes that I have like three. How many head drops that I have like one, two, three, four, five, six, seven, eight, nine. Yeah, that's based on this drawing. But again, I need to be a little bit more careful than that to make like a good square. Yeah, but so let's see, this is the solutions that I have. This is another solution which is more careful than the one I did, like more refined, like you see some good squares here, much better than the ones that I had. But so you can do this, and if you did this, you will end up, so that's like your flow line, that's like your flow line, that's your flow line, and that's like here your equipotential line. And then you know this is like 100, and then you just see how many head drop, and then you can like find the head here, the head here. If I told you what's the head here, like let's say, I don't know, let's say the head here is 99, for example, just for the sake of argument, yeah. And then I told you, so so here is 99, here is 100. Now you can calculate the head at any way you like. Well, if I told you what's the head here, so that would be something between 100 and 99. So that would be 99.5, for example, meter. Yeah, because so now you see that's the way you can estimate the head at any part of your system, or you can calculate discharge also. And this is just like a quick calculation. Like, see, I just did this a quick calculation, and you can use this to explain like for discussion. Like for example, I was once like that example which Iliam Puter showed. I was once discussing this example with a colleague, explaining to him this dike and why you need this dike and why you need to have this longer flow passes so that like the groundwater flow will not overturn your dams that you are building here, and that's why you put like to anchor it here, and then you create this longer ground water pass to avoid like your tilting down. So you can just draw these things and draw it to scale. And then if he told you, okay, can you tell me, for example, something about the flow velocity, like giving or quantities, then you can do this quick, assessment just while you're sitting. Yeah, that's one thing you can use this flow line for. Okay. Here is another example, like a sheet pile. So that's how you will draw your flow line and flow net. In this example, like we have like how many flow tube, like 1, 2, 3, 4. How many head drops? We have like 1, 2, 3, 4, 5, 6, 7, 8. Uh, so in that case, the head would be like the delta H would be 8, Q would be 4 times K, whatever the K is. So the Q here would be 4 times K, whatever your K is. Head at point X. So I'm telling you here in this, like, what is the head here at point X? Yeah. So the head here at point X, that's like what I want to show you in this example. I already showed you in the previous example, but I want to show you in this example. So here head is 10, 9, 8, 7, 6, 5, 4, 3, 2. What is the head here? So the head here, it should be like less than 5, but larger than 4 and more toward here. So I will say maybe 4.7, maybe. Yeah, maybe 4.7 or something like this. Or I get an estimation like here's, you have to see it is like this is here, and okay, so like you see this is here and this is here. I mean, you can consider it to be like a little bit like in the middle, like I just consider it to be a little bit. Again, it's not be like here's the answer I gave here was 4.5. The answers that I did now was 4.7. Yeah. But I mean, they are close. Okay. Uh, Now, I want you, this is for your homework, so like you can try to solve this for your homework. Uh, so again, like you have like this is an impermeable bed block, so this is a no flow boundary. Yeah. There's no recharge, so one flow line would be here. One flow line I know will be somewhere here parallel to this, and then maybe you do like another one here maybe, and, and then like flow net, they are perpendicular. So like if I want to do flow net here, what should be perpendicular to this one? So it should be like perpendicular to this one. It should be like perpendicular to this one, and it should be perpendicular to this one. So I will maybe draw like a line somewhere here. But again, it's not like making a perfect square. So, so since it's not like making a perfect square, I might want to move it maybe a little bit here. See, that's how you learn about your flow. Like you maybe move it a little bit here. And then maybe this one, move it a little bit here. See, it's like you have to watch the video. Maybe, yeah, see here. Here is okay. Here, maybe like, so I might need to move this a little bit up, maybe, and move this like a little bit here, for example. Okay, not bad. And then here just need to be perpendicular. It needs to be perpendicular. Here it needs to be perpendicular. You do something like this. Okay, so you can do this and try to solve this, and so that would be like your homework problem. I just give you can start. So like don't like you need to print this. Like you need to print this on a piece of paper and draw it, and then upload your solution on Canvas. If you don't have a printer, stop by my office. I have it already printed. I have like many of them printed in my office. So if you don't have a printer, please stop by my office and I will have it printed for you. Yeah. Okay. I think that's all I think for this video. Oh, yeah, no. Remember, like this was the case that I showed you. This was for we assuming isotropic. What if it is an anisotropic? If it is an anisotropic, you can still like draw like see the flow line are no longer like perpendicular to this, like they are at an angle. And there is a way for calculating this, and you can check this in your textbook. So like you can check your textbook and it will show you how to draw flow line and equipotential line for the isotropic like medium. Yeah, I think that's all for this video. Oh, I think I have one more slide. Okay, let me just do this one more slide. Hydraulic head throughout the system is determined. Like once you do this, flow rate can also be determined. There is a procedure for scaling for an isotropic system. If that's an isotropic system, there is a procedure for scaling. For the case of hydraulic conductivity is heterogeneous, constructing a flow rate require like a numerical method, like a computer software. And I showed you already one of your textbook about this flow line, and flow net has more details about this. I think that's all. So I leave you with these conclusions. You can read them and like see you in the next video.